In the previous lesson, we learned about the convolution of two functions, as well as that the inverse Laplace transform of big F of s times big G of s equals the convolution of f of t and g of t. This lesson will demonstrate the full power of the convolution and the Laplace transform. We can give the solution to the forced oscillation problem for any forcing function as a definite integral. As an example, we will solve x double prime plus omega sub 0 squared x equals f of t with initial conditions x of 0 equals 0 and x prime of 0 equals 0 for any arbitrary function f of t. Recall we first take the Laplace transform of both sides of the equation. We also denote the Laplace transform of little f of t as big X of s, and the Laplace transform of little f of t as big F of s as usual. So again, the first step is to take the Laplace transform of both sides of the equation. On the left, the Laplace transform of x double prime is equal to s squared times big X of s minus s times x of 0 minus x prime of 0, and the Laplace transform of omega sub 0 squared x is equal to omega sub 0 squared times big X of s. On the right, the Laplace transform of f of t is equal to big F of s. And now we perform substitution using the initial conditions. Since x of 0 equals 0 and x prime of 0 equals 0, the equation simplifies to s squared times big X of s plus omega sub 0 squared times big X of s equals big F of s. And now we solve for big X of s by factoring out big X of s on the left and then dividing both sides by the sum of s squared and omega sub 0 squared. This gives us big X of s equals big F of s times 1 divided by the sum of s squared and omega sub 0 squared. And now to solve for x of t, we take the inverse Laplace transform of both sides of the equation. And now let's continue on the next slide. On the left, the inverse Laplace transform of big X of s is equal to x of t, and on the right we have the inverse Laplace transform of big F of s times 1 divided by the sum of s squared and omega sub 0 squared. This is where we apply the property that the inverse Laplace transform of big F of s times big G of s equals the convolution of f of t and g of t. We know the inverse Laplace transform of big F of s is equal to f of t. And now to determine the inverse Laplace transform of 1 divided by the sum of s squared and omega sub 0 squared, we need to apply the first formula in the second column of the table on the left, where the inverse Laplace transform of omega divided by the sum of s squared and omega squared is equal to sine of omega t. Notice in our case that we don't have omega sub 0 in the numerator, but we can write this fraction as the given fraction times omega sub 0 over omega sub 0, and therefore the inverse Laplace transform is sine of omega sub 0 t divided by omega sub 0, which means the right side of the equation is equal to the convolution of f of t and sine of omega sub 0 t divided by omega, or we can change the order of the convolution and write it as a convolution of sine of omega sub 0 t divided by omega sub 0 and f of t. The order of the convolution will affect the solution as a definite integral. Using the first order of the convolution, applying the definition, we have x of t equals the integral from 0 to t of f of tau times sine of omega sub 0 times the difference of t and tau divided by omega sub 0 d tau. Or if we change the order of the convolution, we can write x of t as x of t equals the integral from 0 to t of sine tau divided by omega sub 0 times f of the quantity t minus tau d tau. Again, the second integral comes from using the convolution in the order shown here on the right. There's one more thing to notice here about this example. We can now see how the Laplace transform handles resonance. Suppose that f of t equals cosine of omega sub 0 t. Then we have x of t equals the integral from 0 to t of sine of omega sub 0 tau divided by omega sub 0 times cosine of omega sub 0 times the difference of t and tau d tau. We can factor out the constant of 1 over omega sub 0 and write this as 1 over omega sub 0 times the integral from 0 to t of sine omega sub 0 tau times cosine of omega sub 0 times the difference of t and tau d tau. Recall in lesson 6.3.1, we computed the convolution of f of t equals sine 2t and g of t equals cosine 2t. And let's go back and take a look at that work. Here's the work for the convolution of f of t and g of t when f of t equals sine 2t and g of t equals cosine 2t. Notice the convolution is equal to 1/2 t times sine 2t. So going back to our lesson, When we have a fraction of 1 over omega sub 0 in the front and 2 is equal to omega sub 0, we have x of t equals 1 divided by omega sub 0 times 1/2 t sine of omega sub 0 t, which we can write as 1 over the product of 2 and omega sub 0 times t times sine of omega sub 0. Notice the t in front of the sign. The solution therefore grows without bound as t gets larger, meaning we get resonance. Similarly, we can solve any constant coefficient equation with an arbitrary forcing function f of t as a definite integral using convolution, as we did above. A definite integral rather than a closed form solution is usually enough for most practical purposes. If not, we can numerically evaluate any definite integral. I hope you found this helpful.